history of science is basically irrelevant. If one person doesn't find something, then someone eventually will. I was like, yeah, exactly. If it wasn't Euclid, somebody would have figured out, or somebody would have formalized Greek mathematics around the same time as him. It would have only taken maybe another 100 years or so to like get somebody who was sufficiently motivated to do it. And keeping in mind, this is like 500 years after Pythagoras, so it wasn't him. Goodness knows he was not interested in that, considering how much debauchery he was getting up to in his day. That also usually gets a "wait, what?" from students. Okay. So anyway, if we want something that is non-arbitrary, then we say, okay, what measurements are non-arbitrary about this thing? Well, we've got a radius. And we've got circumference, which are really the two big ones. Getting insects from outside. I'm wondering if something just got me in the nose. Could just been a hair, I guess. I don't know. All right. So in terms of circumference, we have a relationship between circumference and radius, right? Circumference is equal to 2 pi times our radius. And if we let r be equal to 1, then our circumference here is just going to be 2 pi. So, like, cool. Let's go down here, and we could say all of our individual sectors, so all of these areas that we've created within this circle, can now be measured not just as an angle in degrees, but also in an angle as far as how many radii are we traveling around the outside of the circle to get to whatever location we're at. And it doesn't actually matter what the size of the circle is. So here we can either be at 0 or we go all the way around and we get to 2 pi. Right, if we only go halfway around, that's going to be pi. If we only go a quarter way around, that's pi over 2. And at the bottom here, this is going to be 3 pi over 2. Some other mathematicians have been interested in making this in terms of tau, which is just you go from 0 to tau, 0 to 1. So 2 pi is equal to tau, and then you're just saying how many, like, what fraction of the circle are you going around? And that's your tau. That's your angle. It works. It's fine. But if you want to do that, then you've got to redefine all of trigonometry to be based on tau instead of pi. And, you know, it's fine. It works. It's just a scale factor of 2, basically. Okay. So then we've also got these angles here. Close enough. Right? So now if we divide each of these halves up into halves, this is going to get us pi over 4. And then we can count, because these are all going to be equal going around. So starting from 0, we go to 1 pi over 4, 2 pi's on 4, which is the same as 1 pi over 2, 3 pi's on 4, and again, I'm just counting and using pi over whatever as a unit. 4 pi's on 4 is the same as pi, 5 pi's on 4 gets us down here, 6 pi's on 4 simplifies to 3 pi over 2. 7 pi's on 4 gets us over here. And 8 pi's on 4 gets us back to 2 pi. So we're back at the beginning. Okay, and then if we cut this segment into thirds and actually cut the segment around here into thirds, yeah, there's a reason. We'll talk about it. Hey guys, hang on one sec. I got a visitor. Oop, kerclunk. No, give me one sec. Alright, I'm gonna hit the button and we'll go for 3 more minutes and be right back. Alright, thanks for sticking around. Yeah, that was a lot faster of a visit than I was anticipating, so apologies for hitting the 3 minutes, I suppose, but yeah. You never know with them sometimes. Okay, so what we've just done here, and I popped in a couple of these while we were out, is that we've now split our pi into 6 equal parts. So here, this is going to be pi over 6. And now we can go, again, the same counting mechanism. This is going to be 1 pi over 6. 2 pi's over 6 is going to be pi over 3. 3 pi's over 6 is equivalent to pi over 2. 4 pi over 6 is equivalent to 2 pi over 3. 5 pi over 6 is here. 6 pi over 6 is just pi. 7 pi over 6 is here. 8 pi over 6 is is equivalent to 4 pi over 3. Oof. Yep. 9 pi over 6 is equivalent to 3 pi over 2. 10 pi over 6 is equivalent to 5 pi over 3. Damn it. Whee! And my head's clear. Good. 11 pi over 6 is going to be here. And 12 pi over 6 is back to 2 pi. So with that, now we see we've got all of the individual values that we're honestly going to need. I also usually include the other ones. What? That was not what I wanted to do. Now you can see how straight I draw one and just jab out like this. Here. Here. Nope. Here. And here. And it's off a bit. All right, these are our pi's on 12. And if we're honest here, right, this is our base unit. This is going to be 1 pi over 12. 2 pi over 12 is pi over 6. 3 pi over 12 is pi over 4. 4 pi over 6, 4 pi over 12 is pi over 3. 5 pi over 12 is its own thing. 6, 7 pi's on 12. 8, 9, 10, 11. 12, 13. 14, 15, 16, 17. 18, 19. 20, 21, 22, 23. And 24 pi's on 12 is back to 2 pi. So I prefer to have students build this one out first as we go through and say, like, okay, these are all of our kind of base units. It's a multiple of pi on 12. Yep, exactly. But the thing is that the pi's on 12 that are not simplifiable, so our 1, 5, 7, 11, 13, 17, 19, and 23 pi's on 12, are really hard to find any sort of angle stuff for until we get like halfway into the course. It's like a third maybe, but nonetheless, it's for me, it's unit 2. So we look at this and we say, okay, we can split it up in terms of pi's on 12, right? Our pi value, 180 degrees, ends up getting split into 12ths. Those are 15-degree segments if you're going by the degrees. So, yeah. Not multiples, increments. Okay, they're all 15-degree increments going all the way around if you prefer degrees. If we're doing radians, they're all pi on 12 every single time. And a reminder, this is pi on 12 radians, which means that this is 1/12 of That's not true. It's sorry, pi on 12 is approximately 1/4 of a radius measurement. So whatever your radius measurement is, it's like give or take a fourth of that. Again, 3.14159 over 12. Okay, so when we do this, we're going to say now, well, depending on how big the circle is, that's an actual different distance. So if it's, unit 1, we're on the unit circle, and so that distance here is this arc. If it's way out here, it's the same arc, but now it's further away, so the actual physical distance is going to be bigger. So, like, how do we do that? Well, if we look at this, right, we've got 2 pi times r was going to be our circumference. And some of you may already see it. Circumference is equal to 2 pi times r. So what about, like, any old random arc length? We'll call it s. Well, we've got our radius here, but that just meant, like, how far out do we go before we make that arc? Circumference is going 2 pi. That's the whole distance all the way around. So, like, half of it would only be pi. A quarter of it would only be pi over 2. You know, some random measurement like here, wherever that is. If we went like that, we're going around the outside of the arc here, it'd just be the radius times whatever this thing is, right? So this is our angle. Right? Our arc length, the length around the outside, is just going to be our angle in radians times the number of radii. Okay, I'm going to take this out very carefully. Probably don't need to. Okay, so that's going to be what we get for this. Now, what we're going to do is we're going to say, now we want actual, like, physical locations in terms of how we get nice values on this circle. Okay, well, how do we get nice values on the circle? And I use the word nice in quotation marks here because it kind of depends on what your definition of nice is. We do know that if you should just go out with, if you have any particular triangles that you know, right? 45, 45, 90. Is a particularly nice kind of triangle. It has an angle which is half of a 90-degree angle. So we know that 90-degree angle is pi over 2. So half of that arc length is half of the angle, pi over 4. Same deal. So a 45, 45, 90 triangle, we can look at this and say, all right, I know that my radius is 1. Or you can just make it r if you wanted to, but we'll stick with unit circle for now. Well, how much is our x and y coordinate going to be worth? If we remember from geometry, anytime you have an equal angle in the same triangle, the opposite sides to those angles have to be the same as well. So in this particular case, we've got this 45, 45, 90 triangle. Wow, okay, close enough. X, y, and 1. If the angles are the same, then x is equal to y. And so we end up with x and 1. From the Pythagorean theorem, we know that x squared plus x squared is going to be equal to 1. So this is 2 x squareds, which means that x squared has to be a half, which means that our absolute value of x, right, the actual value that we have here, has to be the square root of 1/2, which is equal to square root of 1 over square root of 2, or just 1 over the square root of 2. Or if you insist, square root of 2 over 2. We can rationalize the denominator, multiply by square root of 2 over square root of 2, and get that. So either way we get with this, we get these values. And interestingly enough, right, this is the absolute value of x. So the distance that we travel from the origin in the x direction needs to be square root of 2 over 2, or 1 over the square root of 2. Now, if that's the distance that we travel in the x direction, that doesn't matter which direction we go.
Raiding party!
Raiding party! Hey, Stucky, how you doing? Good evening and welcome, everybody. My name is Obi-Wan Pez. This is N Simplex Pachinko. We are working on some trigonometry, so kind of the introductory section of trigonometry. How exactly are we going to get this baseline? Good evening. How are we going to get this baseline knowledge of how trigonometry works? So we're going to start, well, we're starting with the unit circle and then going to work our way up from there. So good evening, everybody. Hi. Phobos, how you doing? This is the information for Ian Stucky. If you have at all any interest in hanging out with other cool math type people, that is their information. We have Stucky has a Discord server, and that is the Twitch channel up above. And Nep, double dipping. Always encouraged. I will say, right? Always encouraged. Some people think it's a bad idea. I definitely don't. Get any and all information that you possibly can. Right? So this means that our x can be either a positive or a negative root 2 over 2. Now that also means that since x was equal to y, that y is also either positive or negative root 2 over 2. And this then means that we can go in any one of these directions. Alright, now I will say, right, if it said, technically I said x equals y, we didn't really have to just be x and y being the exact same number. They could just have the same value. So realistically, it was just that the absolute value of x and the absolute value of y, their distances, were going to be the same. So even though we did say originally x and y were the same, that's not really what we meant. That was only true for the one in the first quadrant. Let me actually pull my mouse closer so I don't keep having to lean off screen. Right? Our x and our y have to be the same distance, but we could have been going down here into quadrant 4, make a 45, 45, 90. Could have gone into quadrant 3, could have gone into quadrant 2, anywhere we wanted. Our x and our y just have to have the same distance. Okay. So y is going to be then equal to plus or minus root 2 over 2 as well. So this gives us 4 different possibilities for having these sets of coordinates. Again, here we get root 2 over 2 comma root 2 over 2. Whatever. Here we get root 2 over 2 comma negative root 2 over 2. Down here we get negative root 2 over 2, comma negative root 2 over 2. And up here, we get negative root 2 over 2, comma positive root 2 over 2. And again, we could have done this as 1 over the square root of 2 instead, but yep. Okay, so that's how we're going to work on 45, 45, 90 triangles. So then the other one is, well, we do know some sort of relationship that exists with equilateral triangles, right? So it'd be really nice if we could set up an equilateral triangle inside of our unit circle. Oh, what do you know? We can. Right? We know that equilateral also means equiangular. And so if it's equiangular, then they have to be 60 degrees on each corner, which also means that these are going to be, 60 degrees was 360 divided by 6. So now it's 2 pi divided by 6. 2 pi over 6, we did that earlier. It's pi over 3. So we can make pi over 3 on any one of our angles there. And looking at it from that perspective, let's chop this thing in half this way, because again, that makes us have a right angle triangle now. And for our equilateral triangles, if we're doing this on let's do it on 2 pi over 3, because otherwise we got some stuff that might be in the way. Here, this is going to get us an equilateral triangle. If you're not convinced that, oh, well, this one's not going to work, like, how do you know that that's going to land exactly on, this point out here? You might say, look, you just invented that. I don't believe you. That's fine. We'll do it this way instead. So a 30-degree angle is pi over 6. So we'll go pi over 6 up and pi over 6 down. I know for a fact that this point here and this point here have now landed in the same horizontal place because their angles are equal going up and going down. Again, this is our pi over 6 here. This is pi over 6 here. So these are equal, which means that our sides must be equal here and here, right? Split along our x-axis. Okay, well, split along the x-axis. If our equilateral triangle, and you can tell this is not an equilateral triangle just by looking at it. My drawing is terrible, but nonetheless. We're going to say, well, our radius was 1, so this radius is 1, and since it's an equilateral triangle, our third side must also be 1, which we just split it in half. So the top one's a half, the bottom one's a half. Cool. Those are our y values for those 2 points. Positive 1/2, negative 1/2. Now, about the x values, that's where it gets a little harder, because now we got to look at, like, how far over is it? It's not 1, it's not a half, like, well, these are vertically distance of a half. That's another thing you can check, by the way. Does it even look like a half? We go across like this, check like that distance here, say, yeah, more or less. It's close enough. Okay, but enough of that. So what we're really concerned with in terms of like actually getting these coordinates is that we've made some yeah we've actually made this equilateral triangle, which then gets split in half. So now we've got a half and a half up and down. Then that leads us to a picture, which we can draw somewhere like this. So we've got a half here and a 1 there. And now we don't know what the x value is going across. I want to remind you that this is the same thing if we took this whole thing and rotated it and made it connect with 2 pi over 3 or pi over 3 or anywhere else on the circle. Like it's the same triangle, it's just how you organize it. It's going to look a little bit different.